Okay, so in the last video we stopped at this topic, the switching threshold. So let's continue with the switching threshold. It's a very important concept that we need to understand. And okay, so switching threshold VM is where V in equals to V out, where both the PMOS and NMOS not linear, since the VDS is equals to VGS. So what it means V in V out means that your gate voltage is exactly the same as your drain voltage on the inverter. So if you remember the previous slides, so at VM, whereby V in equals to V out, we can say that both of the device can be in velocity saturation. Okay, it could be in normal saturation as well, but let's assume that 1.25, okay, 1.25 volts VDD over 2, and most likely is both devices going to be in velocity saturation, which means that we have current flow in both the PMOS and the NMOS. Okay, so here is given that VM is approximately equals to R VDD over 1 plus R, where R is given by this equation Kp VD sat P over Kn VD sat N. Okay, so if you remember, Kp here is Kp here is your gain factor. So it's actually Kp prime W over Lp. Okay, and Kn is Kn prime W over Ln. Okay, so basically the switching threshold set by ratio R, which compares the relative drive strength of the PMOS and NMOS transistors. We want Vm equals to VDD over 2 to have a comparable high and low noise margin, so we want R equals to 1, approximately equals to 1. So how do we set, what can we control if we want R equals to 1 here? Okay, we want R equals to 1, so means Kp VD sat P has to be equals to close to Kn VD sat N. Okay, so Kp prime is constant, is given to you by the process. Kn prime is given to you, VD sat P is given, VD sat N is given. So the two parameters that we can control to have Vm equals to VDD over 2 is actually WLP and WLN. Okay, so that's why we can control how our gate, our inverter behaves by looking or modifying our size of the PMOS and NMOS. Okay, so let's look at this example. For the following 0.25 micron CMOS process parameters, we can find W for PMOS to ensure Vm 1.25 volts, given VDD 2.5, WLN 1.5, LPLN 0.25. Okay, so here is given to you the parameters. So we have a VTO, we have gamma, VDSAT, K prime, and lambda. Okay, for both NMOS and PMOS. And the key thing here is, if you see, is given to you that the size of your NMOS is 1.5. The ratio of the size W over L for the NMOS is 1.5, and we want to know what should be the size of your PMOS such that we can get Vm equals to 1.25. Okay. Okay, so we assume both of the device in velocity saturation. So what is the current equation? So we know that the current will flow through both the PMOS and the NMOS, and the current equation we're going to use is the current in the velocity saturation region. So what is the equation for current in the velocity saturation? So ID, let's say N, okay, through the NMOS in velocity saturation is simply Kn prime W over Ln, okay, VGS minus VT, and then we have VDSAT minus VDSAT squared over 2. Okay, and let's ignore our channel length modulation, so we're not going to put, okay, normally we'll have 1 plus lambda VDS, and let's I think in this equation they ignore this one. Okay, if they say don't ignore, then you need to put that one there. Okay, so if you look at this equation here, so we equate the two currents together. Okay, so let's have a small visualization here of what's going on. Okay, so here is your out. So you have a current flow like this and a current flow like this through the NMOS and PMOS. So here is IDN, IDP, and here is your IDNMOS. Okay, and here is your VDD. Okay, so the current IDP must be equals to IDN. Okay, so here is your IDN and here is your IDP, and we see WLN, this is your KN prime 115. Okay, and then you have the KP prime. 0.63 here is coming from here, your VD sat N. Your VD sat P is -1, so just one there. And if you do this calculation correctly, you're going to get 3.48, and 3.48 is the WL ratio between the P and the N. Okay, WLP divided WLN is 3.48, so WLN is given 1.5. So if you put 1.5 here, okay, you put 1.5 there, 3.48 times 1.5, you get 5.23, and we know that your LP, okay, LP is 0.25, therefore we know our WP 1.3 micron. Okay, so let's look at what's going on here. So we go here, W over Ln is 1.5, and your WLP is 5.3, and we can say that WLP is roughly 5, maybe 3.5 times, right? 3.5 times of WLN. Okay, so we are saying if the LP and LN is the same, so you can say that the width of the PMOS is around it should be around 3.5 times bigger than the NMOS. Okay, in order to get VM 1.25, because if you don't follow this rule, if you just make WLN equals to WLP, then most likely you're not going to get VM 1.25. So what's the impact if your VM is not 1.25? Okay, so remember we have the noise margin. Your noise margin will not be the same. You're going to have a longer logic 0, okay, compared to logic 1, or vice versa. Longer logic 1 compared to logic 0. Okay, so it's very important to analyze this, to know that you want to get the middle ground, same noise margins, and how do we calculate it? Looking at the drain current going through both the NMOS and the PMOS, and we can calculate our size of the transistor. Okay, so here so VM here is actually is an approximation. So actually you can use a more accurate VM. Okay, so we can use a more accurate VM here. Okay, do we need to memorize the equation? No. Okay, so one thing I want to mention here before we go on, I just discussed with the Prof Abu, and most likely for your test 1 is going to be open book and open notes, so you are allowed to have access to the internet and so on, since everybody is working from home and we cannot really control. So you have access to all the equations here. I mean, if you need to use your VM or whatever equation, everything is in the notes, so you can use during your test. Okay, so let's continue with this. Let's have a look at how does the size impact your VTC, your voltage transfer characteristics. Okay, so here is a VTC of 5 different inverters with different sizes of WL and WLP. So for example, here for A we have WLN equals to 10 and WLP 10, and here B WLN 5, WLP 10. So you want to know which one is A. Okay, A is it number 1, number 2, or 3, 4, or 5, and B, which one? So you want to try to match and see how does the ratio, the relative sizes of your PMOS and NMOS will impact your VTC. Okay, so let's have a clear picture here. Let's draw our inverter again here. Okay, so basically what we are trying to show gate, and this is your out, or you say your in actually. Okay, so in out, V in, V out, VDD. So in A you have your WLP is 10. Okay, and your here is also 10, so your ratio is 1, 10 over 10. Okay, your P to N ratio is equals to 1. And for B, C, D, E, so for B, you have a 10, 5, and C, you have a 5, 10, and D, let's see, 2, 10, E, you have a 10, 2. Okay, so your ratio here is 10 over 5, 2, 0.5, 0.2, and 5. Okay. Okay, so which one has the highest ratio? Let's look at the highest ratio first. So the highest ratio is actually inverter E. Okay, inverter E highest. And which one is the lowest? The lowest ratio is D. So here is lowest. Okay, so now we have the highest. We just need those two, and then we can easily do it. Okay, so we have the highest and the lowest. So the highest is a ratio of 5. So we're saying that the PMOS is 5 times bigger than the NMOS. And how does that impact the VTC? Because it will impact our noise margin. Okay, so actually if you go to the next slide, okay, here it says that increasing the width of the PMOS moves the VM towards the VDD, increasing the width of the NMOS moves the VM towards ground. Okay, so let's see what happened here. That if we have the biggest ratio will move your VTC towards VDD. So here is actually your E. Okay, and the smallest ratio is D. Okay, so if you have a bigger NMOS, it will move towards the ground. Okay, so then you can I think you can do this yourself. Okay, so which was the second? Let's see, D, and then this is C, 1 and 2, so this is A and B, 1, 2, 5. Okay, D, C, A, B, E. All right, so let's move on. Okay, so basically VM is relative insensitive to variations in device ratio, means that setting the ratio to 3, 2.5, and 2 gives VMs of 1.2, 1.1, 1.13. What this thing means here is that the ratio is the one that counts. Okay, you can have the size whatever you want, right? I mean, but in the end, it's a ratio that counts, and basically the ratio doesn't really change your VM. Okay, but there is a different impact as you make your device bigger. It will impact the whole circuit, as we will see in the later chapters. Okay, so let's look at the noise margin. So as you see before, why we need the VM, as I mentioned, is why we need the VM in the middle. Okay, is because we want to have equal noise margin, right? We want the same range for logic 0, same range between for logic 1 and logic 0, same range, basically, right? Means that we want to have the same distance between 0 to VIL, which is your noise margin low, and you want the same distance for your noise margin high. Okay, so here is noise margin low, noise margin high, and it's given by this equation. So noise margin low is between VIL and ground, and noise margin high is between VDD and VIH. Okay, so if you can imagine that if you move your VM towards the right or towards the left, then your noise margin will shrink, and the other noise margin will increase, and it's not good. You don't have the same balance. Okay, so So then you can also have this equation here where we can approximate what is the value of VIH and VIL given VM. So if your VM is given, so if your VM is given, then actually it depends on your slope here, right? Your slope there, how slopey it is. Okay, if it's not slopey, I mean it's a very sharp transition, then it becomes almost like an ideal inverter, okay, where your noise margin is huge. So that's another question: how to make your inverter to be close to ideal? Means that the slope is very sharp and your noise margin is big. Okay, so you don't have the indeterminate, undefined region in the middle. So that's one, and in fact that depends on actually the value of G. Okay, so G actually is your gain, which determines the slope of your transition going from VDD to ground. Okay, and let's look at what is G. I think it should be in the next one. Okay, this one is just a plot showing the VTC from simulation. Okay, so G is given by this equation. So G, if you notice here, G is actually negative. Okay, so we have a negative there, and that's why here is actually VIH is VM minus VM over G. So VIH is actually VM plus this part here is actually VM over G. Okay, so VM over G, which is a negative value, so it's VM plus VM over minus G. Okay, okay, so G is negative and it's given by this equation, and remember R is your what the KP VD set, right? KP VD set over KN VD set n. Okay, and here is your channel length modulation lambda, and it depends also on your threshold voltage VTN VD set n over 2. Okay, so again in your test, I mean, if you need to use your G equation, is here, you don't need to memorize. Okay, but you know, if we give probably open book, everything open for your test, and it might be a little bit more challenging. The test will be a little bit more challenging since you have all the equations, but we'll see how it goes. We'll see how it goes with it. Okay, anyway, so G is dictated significantly by technology parameters, especially the channel length modulation. Designer, however, can influence G through transistor sizing and supply voltage. So these two parameters here that can determine, you know, remember what our goal is to get close to ideal inverter, which means we want a high gain. Okay, a high gain, very sharp transition from VDD to ground, and how you control it by the sizing of the transistor and the supply voltage. But supply voltage here we don't really have control. Okay, if it's 2.5 volts for digital at least, 2.5 volts VDD is 2.5. Okay, and then the main thing that we can control is as a circuit designer, you have more control over the size of your transistors, your layout. Okay. Okay, so the impact of process variation on VTC curve. This one I'm going to skip. Okay, but basically when we say process variation, it's an interesting concept here. Is okay, so you can have your device not exactly to the size that you want. So for example, you draw your layout, your PMOS, you want a 5 micron. W equals to 5 micron, and in the end when you fabricate the chip, your chip might come out as 4.9. Okay, normally it becomes smaller. So your chip now, your PMOS now is 4.9, not 5. So how does that impact your VTC? Of course, you know, in your calculation, in your drawing, you did it perfectly. Okay, you want a 5 micron, you want the NMOS 2.5 micron. Okay, but in the end when you fabricate, it's not 5, it's not 2.5, it's maybe less. So then your VTC will shift. Okay, like this. And how about scaling the supply voltage? So How does the inverter operation change? So we can see here in the VTC, we know that the device threshold voltage is constant. Okay, for 0.25 micron, you put in your design, everything. Threshold voltage 0.4 volts, constant for 0.25 micron process. If you change your VDD, then you can see that your inverter becomes more and more sort of like an ideal kind of operations. Okay, as you lower your VDD. Okay, but this one I'm just gonna skip. It's not really important for now for us. Okay, so this one I think we'll go for with the next video.